cat back to the vet so that they can remove his stitches at 2, and I'm sad that that's going to rob me of some study time, but you know, things could be worse.
Yeah.
Hold on, Jack, did you take a look at those math pretests?
Yeah, I looked at them, so I'm gonna study it this after AP, and I have to do it before June 1st.
Oh yeah, that's perfect. Yeah, 2 weeks, it should be all you need. Like I said, if you need any help on that junk, hit me up. What's up, Cedric?
Is this the water jet channel where the...
I heard you start talking and then your mic cut out. I don't know what happened.
I was saying, is this the water jet channel where the tire blows up?
That is this. So today we're going to try and explain that.
The slow-mo guys have a really good video on the same concept with the CDs and records.
Yes, that there is a magic number that you can cross, and when you cross that number, it causes these things to explode. Yeah. It's a difficult phenomenon to explain, but we're going to try and make some sense of it today. You guys can't really do the math for it, but there are some features of this that we can capture mathematically, but you guys can't calculate the speed at which that thing will just explode without a little bit of calculus. But it's still a good thing to talk about to get going today on rotational motion. We'll wait another minute or so, mostly since it's probably going to take everybody a little bit of time to figure out the wackiness going on with that link. Though I went to the other one and I deleted the actual link connection just so that people wouldn't get confused by it.
What was wrong with it?
I accidentally posted the calculus one. I just like didn't copy paste anything new, and wrong thing. I didn't actually put anything new. Yeah, I copy pasted the link that I had used for calculus, but I regenerate a new link and a new password every class for security, so that I don't get the other seniors trying to show up in my classrooms just to like yell a bad word and then sign off. Even though when they do that, they usually aren't smart enough to make a burner Zoom account, because I straight up had one person who logged in with his, it must have been like his mom or his dad's name account, because the last name matched a senior I recognized. And I was just like, lol. Anyway, that is neither here nor there. So hey y'all, yeah, I think I'm sharing, y'all see a skateboard, right? Okay. And so here's the deal. I want today for us to explain the following phenomena. That'll be warm-up item 1, and then warm-up item 2, I have some updates. Past that, today we're just going to try and quick and dirty talk about what we need to talk about in terms of rotation motion, which will be all of the review stuff that we'll be doing for circular rotational motion. Past that, the only other assignment that I'm asking y'all to give me, like final mandatory, is the next free response, which I believe is due tonight, right?
I think it says May 11th. Let me check.
Oh, which that obviously doesn't make sense,
Yeah.
right? I think I might have made it a week off. But yeah, finish that other free response by tonight, and it'll be your last official AP Physics homework. And then, yeah, we'll do updates after we talk about this particular phenomenon. Nonetheless, let's go check it out.
Yeah, it says on Monday. So is it due today?
You know, I'll just say this. I'm going to do the tutorial tomorrow. So I won't change the due date in case you don't have time, but I am going to do the tutorial tomorrow.
Okay.
Let's do that one more time here. So y'all see this video? So we have a hydrojet, we bring it on to the wheel, and then the wheel expands, 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 and then finally bursts. So my question is, we want to use the language of AP Physics to try and capture what exactly is occurring with some good vocab. Hydrojetting is such a weird thing. Yeah, we're going to use a little bit of AP Physics vocab and maybe a little bit of math to try and capture exactly what is going on with that wheel. Why does it do that? What terms are important here? What numbers are changing such that we go from some size to some bigger size and then finally to an explosion? That is the first part of the warm-up, then updates, then we'll go over big ideas for rotation. Where is my screen? That's weird. Hold on. I think my document cam crashed. Nope, it crashed again. It crashed all the way this time. Okay, there we go. Okay, yeah. So yeah, item 1, explain this. So we have a skateboard wheel, which we could affix some terms to or whatever. And then when the hydrojet hits it, it expands until it explodes. So try to explain it in terms of relevant vocabulary, and then we're going to try and parameterize what things we can parameterize about it using the equations that we have access to us. And then item number 2, some quick updates. So update, man. Sorry, I'm trying to find my AP equation sheet. Okay. Anyway, item number 2, yeah, updates. So for all of you taking AP tests, which for this class is all of you, I know all of you have at least one AP test to take, probably more than one. I posted a slideshow that I expect you to read through on Google Classroom about the taking of AP tests at home. It's just like a checklist for you to get ready for your AP test coming up next week. It has all the information you need about test dates, times, rules, regulations, standards, and the big thing is making sure that you have your technology set up, ready to go before you take it. So make sure you read the stuff in there about using the correct browser and having certain extensions uninstalled, because once the test time starts, I can't help you in any way. So I can't even help you with tech questions or whatever. It would be like improper communication. And if you lose any time on technical difficulties, you know, like I highly doubt they would give that back to you. So make sure that you're good to go with that stuff. So double check that you look at the AP checklist slideshow. Are there any questions about that?
The AP Physics test is at 4, right?
No, the AP Physics, and I saw your question and I posted on it. The AP Physics test is at 1 p.m.
On the AP student thing, it says at 4, and it says given by our school.
They have it in Eastern time, Jack.
Yeah, that's East Coast time. I mean, don't get me wrong. If I'm wrong, you stop me. And I don't want to be controversial. But here's the slide on the PowerPoint that I posted. I know it's 51 slides, which is a lot of reading to do, but yo, this can affect all of your scores. You should go through it and read it, though do feel free to skip the slides that don't pertain to you. So like there's one slide that's like, hey, here's what to do if you're taking a foreign language test. Well, I don't think any of you are taking foreign language tests, so you could probably skip that one. Wait, am I sharing the correct screen? Yeah. But this here's, oh wait, this is makeup times. Actual test times, Thursday afternoon time is AP Physics 1 Algebra Based, Thursday, May 13th. And then up here, it says that it's Pacific time at 1 p.m. So it's 4 p.m. Eastern where the servers are, but it's going to be 1 p.m. our time. Yeah?
Yeah.
Yeah, okay. Yeah. So, yeah, like I said, go through this. Is boring, but yo, don't make a mistake that causes you to not get scores, you know? Then really none of this was for anything if you can't at least follow this last set of instructions correctly. Item number 2. I just want to do a quick reminder about the time that we've set aside for ourselves to be ready and feeling good about taking the AP tests next week. So just a quick reminder that we're going to be having no class for a while, and then when we do come back, we're going to come back to fun stuff. As soon as I can, I will go over the answers to the AP test as far as I am able to divine them, right? Because the official guidelines won't be up for a while. But, you know, I'm a physicist. I'll do it just for fun and guess what the point values are. We'll do that when we come back. We'll also spend 2 days doing... Do any of y'all subscribe to Bon Appetit?
Yes.
Okay, tight. Bon Appetit is fun. It's really good stuff. I really like It's Alive with Brad. And I'm going to do some Bon Appetit type trash videos from my kitchen downstairs because I promised y'all coffee tutorials. And I guess here's the trade-off. In exchange for not being able to taste the coffee from the coffee tutorials, or even worse, you won't be able to smell it, the coffee tutorials will go up on YouTube and they'll be available forever, I guess, for you. But I'm going to bring both of my camera setups downstairs for AP Physics for a few days, so both the dock cams to point at one thing and then the laptop to broadcast it from. And I'll walk you through 3 different coffee procedures along with some science about why I do them the ways that I do them. I'll try and set up the kitchen nice so it seems semi-professional.
Do you watch the gourmet videos?
Yeah, my wife is addicted to gourmet makes. She watches all of them from start to finish.
Oh, good.
Oh, good.
Yeah, they're really good. I like making pickles, so I actually really like the It's Alive videos. I'm growing some jalapenos right now, and then once they're fully grown in they're getting close. They're like 2 weeks away from being harvested, I think. I'm going to pickle all of them, and then I'm going to drain it, and I'm going to use the pickled juice to make one kind of hot sauce, and then I'm going to use the actual flesh to make another kind of hot sauce. Going to make some homemade hot sauces while we're stuck at home, because what else is there to do?
Why not?
Yeah, might as well get good. And then, yeah. So in terms of this class, right before that, we're going to have a bunch of time off because I ain't trying to like sucker punch you while you're down. So we're going to have no class on Thursday. I already said that because I have to take a test. But next week, there's no class this Thursday. And next week, Monday through Thursday. Just because, you know, you guys either have an AP test on each one of those days or you have an AP test the next day. Are there any AP tests I'm missing? Do you guys have any obligations second week? Also, it just got dark in my room. Anyway, yeah, is that enough time off? Do you guys need any extra days off aside from what I've listed here? No? Okay. Well, then I
Mr.
also
Rob.
yes.
Sorry, I have one question.
Uh-huh.
For Thursday, you said we don't have class. Is that just for physics or for calc too?
Oh, that's for the whole day. That's for calc, because on Thursday I take a test starting at 10 a.m. and I won't be done until 6 p.m.
Oh, it's
so,
okay.
Yeah, I'll just be dead and gone.
All right. Thank you.
Yeah, and so in order to make up for that missed day, and also just because we probably would have done it anyway, we'll be holding office hours outside of our normal time. So this Saturday, I'll be holding office hours. I gave you guys the hours yesterday, right? What were those hours?
I
I think 12 to something. Let me see. 12 to 4.
Yeah. So Saturday, basically the whole afternoon, if you're available, I'll be here to answer literally any and all physics or college or whatever questions you have, even if you just want to stop in and say, hey, I'll just be on Zoom this whole time, and if nobody's here, I'll just build my village in Stardew Valley. And then also Wednesday, we don't have class, but I'll still hold my office hours then as well. So on Wednesday, you guys have the AP English test, and then in the afternoon, I have a final. I have a final from 2:30 to 4:30. So I'm going to hold office hours on Wednesday right after my final is over at 5. I'm just going to take 30 minutes so that I can like get my mind right before I start trying to talk at all of you. And then this will wrap up the class. I thought about doing a practice exam, but to be honest, with the free response that we've been doing, we've basically done 3 or 4 practice exams over the course of the last 3 or 4 weeks, because the full-length test is basically going to be comprised of just 2 of those types of questions. And I don't want to like burden you guys with any extra garbage right before the end. Like I said, be sure to keep doing the review work that you're doing. Most of it is on you, so that in the end the accomplishment is yours. And please do use your lab notebook as a crucial reference, because they will ask you a question. And if we get lucky, man, it might be about one of the labs that we did. I have had years where almost the entire class gets a 3 just based on the fact that one of the free response questions was verbatim a lab that we had happened to do, like I had bet right that year. So if that happens, man, we'll all be like sailing through. Hopefully, man, I hope they pick one of those good ones. If they do that, like, I think the best one was the oscillator lab, the one with the like 3 different pieces, the one with the cart that went up the hill back and forth, the one where it was just a hanging spring, and then also the pendulum. That's a good one. I could see them asking about some of that junk. Anyway, let's try and talk about this. So there are 2 different ways that we could phrase it, right? There is one, the driving of the rotation itself. So why is it that when I have a wheel and we hit it on the edge downwards with a jet of water, why does that cause it to spin? And then number 2, after it picks up enough speed, it then goes faster and faster and faster and faster. At some critical speed, it expands. And then once it expands, after that, there is another critical speed, whose line we cross, where it just freaking explodes, right? And so let's try to explain this. Let's explain that first thing first. So what about the water jet is doing what to the wheel, is driving what kind of rotation? What's happening here?
Like the water is accelerating the wheel.
Let's get really too specific because we're doing physics. So what about the water is rotating the wheel?
Like the pressure?
Yeah, so the water has a large amount of pressure, and this is not a term that y'all need to know for AP Physics 1. This is something we would get to in AP Physics 2. Pressure is actually well defined as being equal to force divided by area. So that particular hydrojet, we talk about this junk in American units because this is America, is 60,000 pounds per square inch. That is to say that that water jet in the surface area of 1 inch, and keep in mind that this is an 8.5 inch piece of paper. So this square that I'm about to draw is to scale using this ruler. That hydrojet, if it hit you, it would mess you up. It would blast a hole right through you, because in an area of this size, that hydrojet would push down with 60,000 pounds of force in this like postage stamp size zone. Is that okay? So, yo, this number is huge. Even if you convert it to metric, this number is huge. It's a ton of pressure. So how would I get the force alone?
Multiplied by acceleration.
A is actually area. So this is force per area. And so pressure then multiplied by area would tell us how much force we're applying, where that area is actually the area of how big the hydrojet is. So the hydrojet is pretty fine. They keep it as small as they can to get the pressure as high as possible. But nonetheless, this number is big. It's a big number times a small number. The big number is bigger. You end up getting a pretty large force. And so what about applying the force on the edge of this is going to make it rotate? What do we call a force multiplied by a distance, where the force and the distance are perpendicular?
Work.
Force times distance, where the force and the distance are parallel, that's work. So if I push a block over a distance of 10 meters, those 2 things, that's parallel, that's work. I'm putting energy into that block. But in this case, the radius is one way, and the force being applied on it is the other. What do we get when we do force times perpendicular distance?
Torque.
Different term, different equation. What was that?
Isn't it torque?
That is indeed the torque. So the force from the hydrojet, right? Pressure times area for that hydrojet is applying a force downwards on the edge of a wheel. And when that force is applied on the edge of the wheel, let's say that the skateboard wheel has a radius of r. That's a pretty standard object, actually. You could probably look it up. or I could like go downstairs and grab a skateboard if I was so motivated. Nonetheless, a force applied at the edge of a wheel like this in this perpendicular fashion, this applies a torque. So a torque is applied. And how could we use this torque? How could we use this torque to figure out what is then going to happen to the wheel? Do we have a torque relationship that can help us out here?
Could we use torque equals moment of inertia times angular acceleration?
Yeah, if you want to know how is this wheel going to be accelerated by this torque, we use the thing that relates torque to acceleration. But anybody out there feeling real clever, real fancy, what's the better name for torque is equal to I alpha? Don't get me wrong, it's correct, and it's right. Wait, where is it on the equation sheet? Is it on the equation sheet?
I'm not sure. I just read it off our notes.
Oh yeah, it is. It is. So it's here. So this is torque is equal to I alpha, but both sides are divided by I. So torque, if you multiplied I over, would be equal to I alpha. Torque is equal to I alpha can go by another name. Yeah, and which Newton's law is that?
Second.
This is actually just the rotational version of Newton's second law. And for whatever reason, they've solved it for acceleration. And that's the way they listed it on the sheet, I guess to hide the fact that this is actually just Newton's second law. But nonetheless, yeah, we hit it with torque is equal to I alpha. Torque is equal to I alpha, where in this case, I would be equal to the moment of inertia of the skateboard wheel itself. We could calculate that because it's a fairly regular shape, and there's an equation for a thin hoop. So if we looked up the equation for the thin hoop and plugged in the mass of the skateboard wheel and the radius of the skateboard wheel, we could then generate out this I, this moment of inertia. So we can now take all of these bits and pieces and we can put them together. It's a lot of bits and pieces, so I'm going to label it all out as nicely as I can. So the torque is equal to the force from the hydrojet multiplied by the radius of the skateboard wheel, where the force of the hydrojet is equal to the pressure multiplied by the area. And we just said if we want to know how fast this thing is going to get spun, then the torque is equal to the moment of inertia of the wheel, how much it resists being rotated, then multiplied by its angular acceleration. So this is equal to I times alpha. So if I make that substitution for F, we could take all of the numbers available to us online, the pressure of the hydrojet, the area of the hydrojet's like actual jet, how big of a spot it hits on that wheel, set that equal to the moment of inertia of the skateboard wheel, and that would tell us how rapidly that wheel is going to accelerate angularly. So this is to say that pressure times area, then multiplied by the radius of the wheel, will be equal to I times alpha. So if we want to know how that guy speeds up, we divide both sides by I. And what do you know? We have the angular acceleration, alpha. This is a useful term for a whole bunch of reasons, because this would allow us to plot out how the wheel accelerates over time. Because we could just say that pressure times area times radius divided by moment of inertia is equal to the change in omega, or in angular speed, divided by a change in time. So if you want to know how much it speeds up, all we have to do is multiply both sides by time. So the speed of the wheel at any time is just going to be equal to time multiplied by pressure, multiplied by area, multiplied by radius, then divided by I, the moment of inertia. And all of this stuff works out nicely so that the units are correct and they agree. And all of that is based on basically no information. But all of this stuff is stuff that we could look up, right? Radius of the wheel, pressure of the hydrojet, area of the hydrojet, moment of inertia of the skateboard wheel. We could actually, sitting from here, right, with no access to what's going on in that lab, figure out exactly how that skateboard wheel accelerates over time. Is this first part okay?
Yes.
And actually, this is a little janky. Make sure that your omegas are clearly omegas. You know that they're an omega because they have a loop in the middle. Otherwise, it's a W. And one quick reminder, omega is a vector. Which way does it point in this case? If I drew the skateboard wheel this way, which way does the omega vector point?
Downwards?
Downwards? Like that? Is that the guess? Is that what you mean by downwards?
Yeah, that's what I mean.
So that can't be the way that omega points. How do we figure out the direction that a rotational vector points?
Oh, the right-hand rule.
Right-hand rule, right? So we have to use our physics gang signs. So if you want to know which way a rotational vector points, right, we are going to have to point our fingers and wrap them in the direction of rotation. So that hydrojet hits this way. So the wheel is going to, oh, I don't know if that frame rate captures that. The wheel is going to spin this way. And so we wrap our fingers around the rotation, and that shows that our thumb would have to point, therefore, into the page, right? Looking at a close-up of my hand is really, really strange. But nonetheless, this would be omega into the page based on the way that we drew it. And if you don't know, there are symbols that we use for vectors that point into or out of a page. If you want to represent that a vector goes into the page, we draw an X with a circle around it. And then if you want to say that a vector comes out of the page, we draw a circle with a dot in it. This is something that you'll all see next year in three-dimensional calculus. Yeah, and now for this last part, right? What makes it blow up? What is happening to it? We have to introduce one more concept that you guys haven't learned before, and this isn't part of AP Physics. This is just for your own knowledge. But it has to play a role in our answer, right? So objects have what's called a material strength. And material strength is just a fancy way of saying, if you want to break this object, it is going to require the following amount of force, right? So all of those times that your brain is like, hey, break the ruler, just do it, why not, right? Your brain is actually saying, hey, grab the ruler, test its material strength, why not, right? And the interesting thing about material strength is that not all objects have a purely linear material strength. There are some materials which are not damaged at all by the interaction of it with an object. There are some objects which are damaged by their interaction with every object. Here's one of the most interesting, I think, comparators that we have about material strength. Did you guys know that aluminum has no minimum stress factor while steel does? And here's what that means, like the easiest way I've found to imagine it. If you took an iron bar and you put that thing in a box, right? And then you filled that box with crickets and they just bounced around inside of that box, what do you think would happen to that iron bar after 1,000 years? Like you have an iron bar and crickets are bouncing around in a box with it for 1,000 years. What marks or evidence do you think there will be of this on that iron bar?
Cricket marks.
Do you, like, other than like chemical marks, like, do you think a cricket can dent an iron bar?
No.
Typically no, right? So after 1,000 years, you would pull that iron bar out, there would be no evidence of damage whatsoever. And that feature is why we use steel to make buildings, because it doesn't tend to decay naturally over time, even under a large amount of stress. As long as you don't cross the magic line that causes steel to fail, steel won't age. It won't fall apart because of that. However, here's where that wacky thought experiment comes from. Solid aluminum has no minimum stress factor as one of its features of its material strength. So if you locked an aluminum bar inside of a box with crickets for 1,000 years, it would probably cause that that aluminum bar to collapse. Any amount of interaction with aluminum will cause aluminum to become damaged. It will cause deformations. Those deformations accumulate over time. That's why airplanes don't last forever. I don't know if you guys know, but airplanes have to have their skeletons replaced every 7 years because they're made of aluminum, and the small damage that the wings take from being flown, because as an airplane flies, the wings flex. That flexing causes damage over time, and every 7 to 10 years, they just have to strip the whole airplane, pull out the skeleton, recycle it, and then install a new one to avoid the airplane from falling apart midair. So in engineering, those of you who go on to that, you'll take probably an entire class called material science, which is all about the different physical properties of the different materials, which explains why we use them where. But just know that there is some amount of force that you can apply on an object called material strength. You go over this number for a given object, and it breaks. So what is overcoming the material strength of that wheel?
Is it like the heat?
No, it is not melting. That's an interesting question. It is probably heating up a lot from the interaction with the wheel, but that is not what is fundamentally causing it to fall apart. Any other guesses out there? I'm going to phrase it this way, and this is a good thing to do if you're stumped when you're trying to answer a concept question. Think about our labs. So did we have a lab where we had an object being spun in a circle?
Yeah.
Which lab was that?
Angular rotation.
Yeah, and tell me a little bit about that lab. And if you don't remember, dig up your book. You should have it, and it should be nice and clean because we all should have turned in a video of the final tour of our lab book. If you haven't, please, do it sooner rather than later. It's a free full letter grade. We swung a string on a ball on a string, and what kept it moving in circular motion? What was the string connected to?
Oh, wait.
Yeah, down below we had a hanging weight. Now go ahead and imagine you're swinging that setup and either the string breaks or the weight were to come, the knot holding it were to come undone and it were to fall. What would then immediately happen to the ball?
Oh, fly, I guess.
So not only would it fall, but if you were looking at it from the top down, which way would it go? So we have this ball and the string is cut, and let's say right here it's moving this way temporarily. If the string were cut, which way would it go flying?
Tangent to the circle.
Tangent to the circle. It would continue on this way, and this is 3D, so this is top down. So from whatever height it was at, it would fall to the floor. But from the top down, it would appear as a straight line, but really it would do a little bit of projectile motion. Here's why I ask this. This is exactly what's happening with the skateboard wheel. The skateboard wheel, the bits and pieces, they're getting pushed to the outside by its rotation, and at some point it just bursts and they travel on in a straight line from whatever direction they were going initially. So what is the equivalent of the string for the wheel? Like, what is holding the wheel together?
Would it be the bearing?
That doesn't actually hold it together. That just provides a low friction surface that lets it rotate. But what is holding the wheel together as it rotates?
The only other options I could think of would be the water hitting it or the actual plastic of the wheel.
No, I'm asking what allows the wheel to rotate? Like you spin the wheel and it's one object and it all spins together, right? Typically, those bits and pieces should want to travel off in straight lines. Literally, what holds the wheel together?
The bearing.
No.
That is not what holds the wheel together. That's what allows it to rotate about the center in a low friction way. Keep in mind that objects are molecules, right? So this object here is plastic. It's made of all of these molecules, and they're bound to each other, right? The individual chemical bonds in here are what provides this thing its material strength. So can we all imagine that for whatever this plastic is, right, polyurethane most likely, that if you were to pull on it hard enough, it would eventually break. Now, you would have to pull on it really hard, but we can assign a single number here to the material strength, F sub S, how much force you need to overcome the strength of this material. As this thing rotates, each one of the molecules within it wants to travel on in a straight line. Each one would prefer to keep moving forward, but the only reason why they don't just fly apart at any given moment is the material bonds that connect it to all of the other parts of the wheel. What is the fake force that we say pushes us out?
Centrifugal.
The centrifugal force. So the thing that causes this thing to expand and then finally break is the fact that that fictitious centrifugal force, which for a rotating object, and this is where our math fails us and we would have to turn to calculus, this would have to be either mv squared over r, or I guess I could write this in its angular equivalent. The only thing I don't like about it is that it doesn't use I, but nonetheless, this is also equal to m omega squared r, once omega crosses a certain threshold, once this number goes too high, once m omega squared r becomes greater than the material strength of the polyurethane, it flies apart. Literally, each one of the atoms in it has so much centrifugal force on it, right? This fictitious force that causes it to drive outwards, that once the centrifugal force becomes greater than the chemical bonds inside of the polyurethane, it just blows apart. There's nothing else it can do. This is true of literally all objects. You could destroy any object by rotating it at a high enough velocity. This information also allows us to set an upper limit on the rotational speed of stars and planets, because if you had a planet that spun fast enough, gravity literally would not be strong enough to hold it together in a blob, and instead it would just fly apart and become most likely an asteroid belt. Anyway, that's a lot of physics. Are there any questions about this skateboard wheel, which has a ton of lessons buried in it, or about updates moving forward? No? Okay, so stay strong in there. Only one homework assignment left to go, and we'll start the tutorial on that tomorrow. But today I just want to hit on real quick big ideas about rotation. This one I'm going to keep real sweet and succinct, because honestly, we didn't do it that long ago. It feels like it was 1,000 years ago, but we had the test for this chapter like right before we got sent home. And that wasn't that long ago either. That was like 5 weeks ago. Nonetheless, let's go ahead and do a quick run through of the big ideas, the important stuff. So most of the math in rotational mechanics isn't new at all. If you look at the first two equations right here for rotational mechanics, they have an identical form to the kinematic equations up top. So up top here, they're the same fundamental equations as these two. The only difference is that everything is translated from rotational terms, from linear terms into rotational terms, but our vocab is the same if you just add the word angular. So instead of velocity, we're talking about angular velocity. Instead of acceleration, we're talking about angular acceleration. And instead of displacement, we're talking about angular displacement. A quick primer on that angular idea. Keep in mind, angular displacement is measured out in radians. And I think one of the most elegant ways to keep in mind why we care about radians, why we use them at all. So a thing to remember about radians is that radians don't really carry a unit, because radians, that shouldn't be an equal. Radians convert radial length to circumferential length. This is actually the role of radians in mathematics. If you have an object which is traveling a circular pathway or something which is literally rotating, radians gives you information that lets you convert radial lengths to circumferential lengths. So here's what I mean by that. Let's say that we have an object which is moving along some circular pathway for some reason from here to here, right? And here's what I want to know. What is the displacement? And what is the distance traveled? There's a little bit of mixed review built into that first one. And let's just go ahead and say here that in terms of radians, the distance that we travel around this Pac-Man, this is exactly 3/4 of a circle as it would appear. And what would that be in radians, 3/4 of a circle? How much is a full circle in radians?
2 pi.
Hit that with 3/4, so now it's 6/4.
Mm-hmm.
And what does 6/4 simplify to?
3/2.
Thank you. So this is 3 pi over 2 radians. Notice I don't write radians because it's not actually a unit. So what is the distance traveled? Let's answer this first. Distance traveled. So if we go from here to here around the edge, how far is that? What is that distance? Distance D has to be equal to what, kids? So here's the whole point of radians. They quickly let you get an arc length. So the distance traveled here is just going to be the radius of the circle, whatever that number is, multiplied by 3 pi over 2. So pick a radius of the circle. Choose a radius for the circle.
Like any radius.
Yeah.
Like 3.
Okay. So if this radius here is 3, if this radius here is simply 3 meters, then that means that this distance traveled around the edge of the circle is going to be equal to 3 meters times 3 pi over 2, which immediately gives us a literal number that we can process. This gives us, you could either say 9 pi over 2 meters, or you can say that this is equal to 14.14 meters based on how many significant figures you have. The whole point here with radians is that if you can express this angle in this system, the reason why we use this system with pi's is that multiplying by radius will instantly give you back the circumferential length, and it allows us to use radii and equations of motion to relate movement this way with the overall movement of the object as it spins. This other part has nothing to do with radians, just trivia. What is the displacement? How is displacement defined?
Isn't it like total distance that an object's traveled or something? Like, yeah.
So distance traveled is the total distance traveled, but displacement will give us a different numeric answer here. How is displacement defined technically?
Distance traveled relative to a point, I think. I don't know.
Almost. It's actually defined with subtraction.
Oh.
Original point minus the final?
Yeah, final point.
Initial point minus final point. So if this was our initial point and this was our final point, then our displacement is simply going to be our final position minus our initial position. So that is to say that we don't care about the shape of the pathway that we took to get here. We just care precisely how far we are from where we started. So this length right here would be our delta x, nice and pure. Which in this case, if you think real hard, this is 3√2 meters, which is equal to something that we could also express as a decimal if we were interested. 4.24 meters, if you guys think back to your rules for special right triangles. Nonetheless, the whole point of radians is that if you have some sort of radial measurement and you then need to quickly learn about the circumferential measurement, right? So I rotated a 3-meter stick from here to here. How far did the tip of the stick travel? Radians times radius gives distances. Okay. And so all of these equations that we use here for circular motion, which is to say this guy, 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 all of those equations that I just put a blue dot next to, they all have a correlate in linear motion. And as a result, you are looking for the same thing in the problem, and mathematically you're solving it the same way. So these first two will tell you how an object moves as it spins. If you are given information about an object's rotational speed, acceleration, time, velocity, those terms are related in the same way as kinematics. So we make a have and a want chart. We choose out which kinematic equation we want to use and we use it. One thing that I think is kind of dirty is that here for our regular equations of motion, they give us these two and the third one, the time independent equation of motion, right? But if you remember all the way back to the beginning of the year, we derived the time-independent equation by taking one of these equations and then plugging it into the other one and then doing a lot of math, right? Because these two equations down here have the exact same form, we could do the exact same thing with them, except they didn't do that for us on the AP sheet. They didn't list that out for us. So let's go ahead and make note of that ourselves right now. You could either do the math from first principle, or you could just interpret this equivalently. So here's what that would tell us. Omega squared, the final angular velocity squared, must be equal to the initial angular velocity squared plus 2 alpha delta theta. So this is to say, right, comparing it to this time-independent equation of motion here, the final angular speed is equal to the initial angular speed plus 2 times angular acceleration times angular displacement. This equation is just as true as this one, and it comes from the same place. If you're given a rotation question and it's time-independent, you have this ready to go. This right here is Newton's second law. This is F equals ma, but in rotational terms. So torque is equal to I times alpha. Again, they're trying to be clever by hiding the fact that this is just torque. Sum of the torques is equal to I alpha. They're trying to hide the fact that it's the same as Newton's laws. But you know, we're smarter than that. This is the formal definition of torque. Radius times the force that is applied at that radius will tell us about how hard it rotates an object. So that is to say, the further out you push on a thing, the easier it'll be to rotate that object. So it's harder to resist somebody pushing your hand down when you're trying to keep your arm level, as opposed to somebody pushing in the middle or somebody pushing on the elbow. The further away you are from the axis of rotation, the greater effect that force will have. We tend to say force gets multiplied by the radius at which it's applied, which is why if something is stuck, if you're trying to rotate something, you hit it with a tool that has a longer handle. That's why you ever see those things that old people use to open jars. The whole deal is they have a handle on them that get attached to the top of the jar. The longer the handle, the easier it becomes to open that jar. Wait, you guys know what I'm talking about?
It's like that long thing, right?
Yeah, like the old people. I mean, no offense to the old people in your life who use jar openers. Like, you know, we all need a little help, but this guy is what I'm talking about. So the reason why, yeah, this thing is worth any money is the simple fact that by adding that radius on there, instead of applying your force right at the point of rotation, by giving yourself that handle, it multiplies your force by the radius of the handle itself. The longer the handle, the more the multiplicative effect. And then on top of regular old conservation of momentum, we have angular momentum, which is also conserved. So angular momentum is moment of inertia times omega. And this is the impulse theorem for angular momentum. So torque multiplied by time will add momentum to a system. If you apply a torque for a certain amount of time, it's going to speed it up, and you can use momentum to calculate how much it speeds it up. Keep in mind, this is what justifies the demonstration that we did with the spinning chair with the weights. Who wants to try and recall the point of that demonstration? What is it showing? When you pull your arms in, what happens to your speed?
You decrease your moment of inertia, which increases your speed.
Yep, so that entire demonstration can be captured in this equation right here with one set of color coding arrows. When we sit down in the chair, L is held constant. It can't change. It's held flat. And when we pull our arms in, we decrease our moment of inertia, which proportionally increases our omega. Even though two objects aren't interacting, technically when that happens, it's a type of collision, and we are using conservation rules to come out with the final answer. And then finally here, we have the fact that a rotating object has with it an associated energy. This was really important when we talked about our big example, the rolling race. That is to say, if you think back to our rolling race question, let's say that I have a block slide down a frictionless ramp versus the exact same ramp, except I place on it a wheel, and that wheel rotates down the ramp. Which one gets to the bottom first and why?
The block gets down first because the rolling one has to expend its energy in more ways.
That is very succinct, yeah. And yeah, it's counterintuitive, but the block gets there before the rolling wheel does. And this is really important for a couple different reasons. Now, the reason why this is counterintuitive is that for this to work out in real life, you would need a surface with no friction. There are no frictionless surfaces in real life, which is why we don't expect this to happen. However, if there was truly no friction, if you got it down to zero, if you put a block on like an air hockey table and you did this experiment and you compared it here, this one is going to win. Here's why. Assuming all things are held equal, they're the same mass, they're the same height, this guy has mgh, which is going to end up being equal to 1/2 mv squared. That's just regular old conservation of energy. But if this guy is going to translate down and rotate down, then there are two types of energy here. It's going to be mgh is equal to 1/2 mv squared. But what's the second associated energy?
1/2 I angular velocity squared.
Plus 1/2 I omega squared, which energies can't be negative. So each one of these terms must be positive. So here, if we solve for what this guy's final velocity is, his final velocity is the classic root 2gh. Here, we can also solve for velocity. And here, our velocity will be equal to root 2gh. But what will also have to get carried over to the other side if we were to solve for v, right, is I would have to subtract this garbage over first, then I would multiply by 2, then I would divide by m. So this is going to be equal to 2gh, yeah, minus I omega squared, all then divided by m. And like I said, this is assuming that all of this is held constant. But hey, this is root 2gh. This is root, I'm sorry, there's a wacky parenthesis in there, in case you're wondering what that mark is. That's a mistake. This is 2gh minus a number, right? So no matter what is going on here, sorry, 2mgh, no matter what is going on here, this number must be smaller than this number. So because this velocity is smaller than this velocity, the one with a smaller velocity will take a larger amount of time to get to the bottom. I would make sure to review those notes on the rolling race. We did really extensive derivations for a whole bunch of different i's, because if you can rewrite I as an equation, then you can learn stuff about this system. You can actually get numeric answers. But in terms of what they expect you to know about angular motion, that's about it. Are there any questions about rotational motion? Well, there might not be now, but there should be, which is why I'm holding those 2 extra office hours. Like I said, try to get that oscillation for response done tonight. We're going to begin the tutorial tomorrow, though I'm not going to touch the due date because I know you guys are very busy with all of your AP tests coming up. That tutorial will go on tomorrow and on Friday, and then I'll be done with lecture leading up to the AP test. Best of luck with your studies, and I'll see you all tomorrow.
Thank you.
Thank you.
Yep.